Okay, guys, so let's talk about kinetics, and this is from your book. And I will post this on 2+ portals as a PDF so that you can review it later and take your time. Now, if you'd like, during this lecture, you can stop at any point. I'm not going to read to you all the words on the slide because there's a lot of words. I am going to give you kind of an overview or a summary of what each slide is talking about. So let's get started. So, rates of chemical reactions are pretty important. We know about rates, like if you have a job, your wage is a rate. If you drive a car, how fast you drive your car is a rate. It's something given to you or measured per hour. And so some of those are pretty important to me anyway. And so I think understanding these a little better will be interesting. It will lead into AP chemistry or even into organic if you choose to go that route. So the chemical reaction also has an associated rate. We can see these, and we typically measure these in the very beginning of a chemical reaction because as the rate continues or the reaction continues, it tends to go towards equilibrium, where in a dynamic process, equilibrium has both the forward and the reverse reaction occurring at the same rate. So many factors influence rates, and we're going to talk about how to determine rates. We're going to talk about what influences rates. We're going to get a nice little overview. When you go on to AP Chemistry, you'll get a lot more detail. So there are a couple of ways of measuring rates, and what we've talked about, or the first thing we're going to talk about, will be differential rates. In a chemical reaction, rate is measured by how much a reactant is consumed, is typically the preferred method because its concentration is very high at the beginning of the reaction. And if we look at the product being produced, we're starting at 0 and we have very small numbers to measure, which makes it less accurate. So we almost always measure the disappearance of a reactant. And we do this by gathering data over time. And we typically do this at a specific temperature. The temperature is not a part of the calculation, but if we change the temperature, it will change the rate. So they are temperature dependent. And reactions involving colored species are pretty easy to measure because, like we did in lab, you can use a colorimeter and you could measure that data over time, or you can measure it in various individual rates. If it's something like that produces a gas, then we can measure pressure or volume. So rates do vary over time. That's very important. In the case of reactants and products in solution, the reaction rate typically decreases with time because the concentration of the reactants are decreasing. If one of the species is being removed, like a reactant is forming a gas and it's going from a liquid or an aqueous state to a gas state, then the reaction tends to have a rate that is constant over time. And we typically measure instantaneous rates, and that's a vocab you should understand. And it is the rate at time 0 or at the very beginning of the reaction. In fact, we only look at rates in a very short window at the beginning of a chemical reaction. And the average rate of change is over some time period, and that is included in the unit for the rate. And so it's typically molarity divided by some unit of time. So factors affecting reaction rates. If they're in 2 different phases, then the more surface area they have, the faster the rate will be. If we increase the temperature, the rates generally increase, and that's about 10 degrees, it'll roughly double. And concentration obviously would affect the rate, and the presence of a catalyst will increase the rate, but it will not change the equilibrium concentrations at the end of the reaction. And that's because it causes the energy barrier to be decreased, or the activation energy. So for doing rate laws, we have 2 types of data that you can be given, and it is a mathematical description of how that rate or how that chemical reaction is changing. And the reaction order describes how much of the change is due to each substance in the reaction. We also talk about overall order and individual species order. So the order is typically first order, second order, or zero order. However, you can have fractional and even negative orders. And negative orders indicate that the reverse reaction is favored rather than the forward reaction. So, differential rate laws are where we have individual experiments, and we can compare experiment 1 to experiment 2. If we have two reactants, then A would be held constant. Its concentration would not change, but we would probably double B, and we'd see how that affects the rate. And we can do the reverse then in a second set of experiments, maybe experiment 2 and 3, where we would double A and we'd hold B constant and see what effect it has on the rate. Integrated rate laws are a little different. However, they do the same thing. It's just a different mathematical process. So the rate constants for these rate laws is determined by measuring concentrations over various times, and the rate constant is independent of how we measure it and what the concentrations are. It is a constant for those species in that reaction at that temperature. So here's an example of some data, and we can see from time 0 to time 200, the purple line is relatively flat and has a slope we could measure. And we could figure out the rate of change, and we could just take the concentration here is about, 7.5, and the reaction, this is about 10, and we could then say 7.5 is final minus our initial, which is 10, we'd get a negative 2.5, and then we would divide that by 200 minutes, and that would give us our rate. And the unit for that would be minutes per molar. So you can see here how I can do the same thing with my product. However, it's more difficult because this number is 0. And I'm measuring pretty small numbers. So half-life we've talked about a little bit in nuclear chemistry, and now we're going to talk about it again in relation to kinetics, and we're going to do some calculations of kinetics. And half-life is the amount of time required for the reactants to decrease their concentration by 1/2. And we can talk about how many half-lives has taken place. This is particularly, as I said, related to radioactivity, but we also use it in kinetics. So first order, the half-life is independent of concentration. So this is one where we typically do these calculations with first order equations. And you can read the rest of that. Please do understand it. Ask me questions. Collision theory we're going to talk about in class, and I'm going to stop here. I think this is a good starting point. We'll work some class problems in class. Please ask me questions. Thank you.